Yeah, so I'm going to tell you a little bit about some math modeling of acetaminophen overdose and how if you take too much, it can result in liver injury. So like Lou said, acetaminophen is, pretty much everyone in this room has taken it, right? It's probably the most common drug in the world, and it's really common because it's effective and it's safe at the therapeutic dose. So acetaminophen, in the UK, it's called paracetamol. They're both abbreviations of its full name, which I don't have up there because it's long and arduous. But in this talk, I'll abbreviate it APAP. So some common drug names, Tylenol, Panadol. So pretty much everyone has taken it, whether you know it or not, interestingly, because it's often found paired with other drugs. So it's in combination. There are 600 products in the US over the counter that contain acetaminophen in one form or another, but it's often paired with other things like in NyQuil or Percocet. And while it's safe and effective in low doses, overdoses are the leading cause of acute liver failure. So it's the leading drug for people to overdose on, and it's quite dangerous. So it's by far the leading cause of acute liver failure. Over half of acute liver failures are caused by Tylenol overdose. So it's responsible for some 50,000 emergency room visits and 500 deaths in the US every year. So the overdoses historically were one-time intentional overdoses. So they were suicide attempts usually in the 70s. Increasingly, they're accidental and they're caused by chronic use. So now it's about 50-50 between intentional versus accidental overdoses. And there's this delay until the onset of symptoms. So there's an 18 to 36-hour delay before symptoms are present. So especially for these chronic use accidental cases, somebody might not know that they overdosed until the symptoms develop some 18 to 36 hours later. Symptoms are somewhat vague, flu-like symptoms, though they do include, in severe cases, disorientation, confusion, or even coma, or death in the most severe case. Yeah? They tell you exactly on the package what the safe dose is. Some of the chronic users who overdose, they might be reading the package, but they're double dipping. So they're taking multiple products, not realizing they both contain acetaminophen. But yeah, if you stick to the recommended dose, it's pretty safe, but people don't always do that for a variety of reasons. Okay, so if you do overdose, there's a very effective antidote, N-acetylcysteine, abbreviated NAC in this talk. So it's extremely effective if it's administered early, so some 12 to 24 hours after an overdose. And the liver regenerates, so there will be survival if the damage isn't too severe. But this 12 to 24 hours is interesting, right, because there's this delay until the onset of symptoms. So patients don't always arrive to the hospital in time for this NAC antidote to actually be perfectly effective, right? And also, you don't know how long it's been since a patient overdosed when they get to the hospital, because one of the symptoms is disorientation, confusion, and coma. So it's really hard to get reliable information on the dosage and the timing of the overdose. And as I said, if the damage is really severe and it's too late for NAC treatment, then liver transplantation might be the only way to save the patient. So why is it toxic? So paracetamol, acetaminophen, it's rapidly absorbed in the gut, into the blood, and it's metabolized in the liver. So most of the acetaminophen is metabolized via glucuronidation or sulfation to non-toxic metabolites, so some 95%. Through these two non-toxic pathways, but some 5%, maybe 10%, it's patient-specific, gets converted to NAPK, which is the toxic metabolite. So in smaller doses, you have glutathione in high concentrations within your hepatocytes. So glutathione is the main antioxidant in the body, so it's found in very high concentrations in the liver. And glutathione very rapidly conjugates the NAPK into a non-toxic metabolite. But as your glutathione reserves are depleted, NAPK can build up. NAPK's it's highly reactive, so it starts binding to intracellular components, damages the cells, and can cause liver failure. Okay, so the goal then is to describe this with a dynamical model, so some sort of mathematical model that describes the metabolism and then the resulting cellular damage from NAPK. And then use the model with data. So you can't actually measure the liver directly if a patient comes to the hospital, right? You measure these markers of liver damage. So we want to use markers that are available to clinicians when a patient gets to the hospital to go backwards in time to estimate the time and size of the overdose, and then to use those to go forward in time and figure out if the patient will live or die. So do they need a transplant? So these are the true critical variables, because if the patient comes in sufficiently late and has taken a sufficiently large overdose, then they will have a poor outcome, right? So the outcome really depends on the time of the overdose and the size of the overdose. So how much time has elapsed since the overdose? Okay, so what are these data? So international normalized ratio of prothrombin time is a measure of clotting time. So one of the liver's jobs is to produce essential clotting factors. If the liver's not doing its job, then it's not producing clotting factors, and so it takes longer for blood to clot. So INR will increase. AST and ALT, so these are liver enzymes, or there's aspartate transaminase and alanine transaminase. So typically, so we're thinking of them just as markers. So typically, they're not found in high concentrations in the blood. They're only found in high concentrations within hepatocytes. But when damaged hepatocytes will release AST and ALT into the blood. And then creatinine, which is a little different from these other three in that it's a measure of kidney function. So kidney function also turns out to be important for survival. So it's a little bit separate from the dynamic model, but it turns out to be important for survival. So I'll talk about it later. Okay, so we actually have data then. So we have AST, ALT, INR, and creatinine time series, as well as outcome for 53 patients from University of Utah Hospital. And so the time series, these are real patients. They're typically one measurement per day, though sometimes more often, sometimes less often. Patients at most will stay in the hospital for a week or so, and then they'll either have recovered or they'll be dead. So it happens really quickly. That's why it's acute liver failure. And I guess that's all I need to say about that. Yes? They don't have information about, so it's really hard to actually know what the dosage and the time since overdose. Those aren't known typically because the patient comes in, they're confused, disoriented, or in a coma. And it's just, I mean, we know from other studies that the information you get from the patient regarding dosage is typically not that accurate. So we're trying to estimate the dosage then in time since overdose with the model. Okay, so this is a schematic of the model. So as I told you, a small fraction of the acetaminophen is metabolized to NAPQ. Glutathione conjugates the NAPQ, but if glutathione is sufficiently depleted, NAPQ damages the functional hepatocytes. The functional hepatocytes, meanwhile, are constantly regenerating and producing essential clotting factors, which decay away. Damaged hepatocytes release AST and ALT into the blood, where they can be measured, and they decay away. So we can translate that story then into a fairly simple system of differential equations. So in this case, acetaminophen is only found as an initial condition, and it's metabolized by hepatocytes. So some fraction of that metabolized by hepatocytes is converted into NAPQ, and some small fraction is excreted in intact form. So glutathione rapidly binds to NAPQ, and they both go away, and a small fraction of NAPQ binds to other things and goes away. Glutathione is produced at some rate, goes away from binding with NAPQ, and glutathione is the main body antioxidant, so it's also being used up for other things or being exported from hepatocytes. Functional hepatocytes, we assume they grow logistically with some carrying capacity, and then they die at a rate proportional to the amount of NAPQ that they have inside of them. So they become damaged. And then the damaged hepatocytes decay away, and when they decay away, they release AST and ALT into the blood, which are cleared down to their typical values, which are very low. Clotting factors produced by functional hepatocytes and decays away, and we assume that multiple clotting factors are involved. So INR is inversely proportional to the amount of clotting factor, raised to some power because multiple clotting factors are presumably involved in blood clotting. Okay. It's a parameter. That should also be a parameter. So there are maybe 4 typical clotting factors involved in blood clotting. There are more. It's another parameter. Yeah. Right. Okay, so we can estimate all parameters in this model, get a pretty good feel for all parameters on this model, irrespective of patient survival information. Okay, so a whole bunch of the parameters are known from the literature, And then 6 parameters we can estimate from properties of the data, but not looking at patient survival information, right? So things like maximum and minimum AST, ALT values, timing of the peaks of AST and ALT. And then these 2 parameters are really just scaling factors. So we can scale so that a 6-gram overdose depletes glutathione, and a 20-gram overdose is equivalent to death. So we're assuming, well, it's thought. This is another parameter. It's thought that you need 30% of the liver to survive. So 70% necrosis is associated with death. Yes? These are time series. Yes. Measurements? Since I went very fast. Oh, I would have to count. So there are only 8 that we can't get from the literature. What's the question? Yes. Well, I'd have to count. I don't know exactly. I mean, and then there are a lot of variables you could non-dimensionalize away, right? I mean, this is really one variable. But there are how many variables or parameters? Well, the variables, I guess there are 1, 2, 3, 4, 5, 6, 7, 8, 9 variables, right? And then parameters, we'd have to count them. So yeah, so all parameters except 8 are known. All except 8. So they know things like the regeneration rate of the liver, the decay rates of AST and ALT and INR. These types of things, a lot of these things are known. Yeah, so I wanted to parameterize this model fully so that the model only depended on initial dose and time since overdose. Okay, so this model, so this is just a sketch of how we parameterized it, right? So many of the parameters, almost all of them, came from the literature, but then a few things like maximum, you need to know how much AST and ALT are released into the blood for each damaged hepatocyte. And you can estimate that from peaks of AST and ALT from the data.
So this does take into account differences in the patients, things like body weight?
Not explicitly. Not explicitly. So this is a characteristic patient. The truth of the matter is, I mean, I can talk about this more later on. I wasn't planning to, but it's really some effective dosage that we're estimating, right? And so the dosage presumably does depend on things like body weight, or there's different mutations that make people process acetaminophen differently. But because we're estimating these from the patient data, it's really we're estimating the amount of liver damage, or the amount of NAPG that's unconjugated by glutathione. So it's really an effective, I mean, you can non-dimensionalize the system, right? And it's really an effective dosage. Any other questions about this? Okay. Yeah, the main point I wanted to make is we can parameterize this irrespective of patient outcome fully. Okay? So these are just some typical marker dynamics for a 20-gram overdose with no treatment or with treatment after 12 hours, or a 10-gram overdose with no treatment or treatment after 12 hours. And you can see AST increases faster than ALT, so there's more AST in each hepatocyte than ALT, and then they decay away, and AST has a shorter half-life than ALT. So this is based on the model. This is model. This is all model. So the point I want to make with this slide is just that the timing matters for the AST, ALT, and INR values, right? So the model only depends on this amount of the overdose and then how long it's been since the overdose. So the AST, ALT, and INR values depend how long it's been since the overdose, right? So just because they're low doesn't mean the patient will have a good outcome. They may have had a large overdose and it's just been a long time. But it's really the relative values of these things that matter. Okay. Okay, so this was the goal that I mentioned earlier, is to go backwards in time to estimate time since overdose and size of overdose, and then use that to estimate outcome. So the dynamical model only depends on the size of the overdose and outcome, or the size of the overdose and the timing of the overdose. Those are the only two things that the dynamics depend on. So we can just use weighted least squares then to estimate to fit the time since overdose and the overdose amount from actual AST, ALT, and INR data. Okay, so this is just using weighted least squares to estimate this because the dynamics only depend on the timing and the size of the overdose. Make sense? Okay. And then we can use post-treatment model fits to get at the weight. So you need some measure of how close you expect the model to fit the data. So we can use post-treatment data to do that. So explicitly, maybe I'll go through AST, but not the others. So post-treatment, if we assume treatment's perfectly effective, then n is 0 post-treatment, and the model reduces in complexity to just a two system or two equations. And so you can fit the model, which only depends on so the post-treatment model, which only depends on the S and Z on admission to the actual data, and then the weights are how close it actually fits, right? So they're the standard deviation of the residual of all measurements of all patients. And so you can do exactly the same thing for ALT and the same thing for INR, except for INR, it depends on 3 variables. But it's basically the same thing. So that gives us the weights for this weighted least squares problem. And then we can get outcome based on the overdose amount and the time since overdose based on whether 70% necrosis occurred. So for a given overdose amount and time since overdose, has there been sufficient liver damage to cause death? So that's how we get outcome from a given estimate of overdose amount and timing. Okay, so this is just a summary of what I talked about. I just try to make it make sense. So if you start off with a patient, AST, ALT, and INR, the curves, so the dynamical system, describe a family of curves. So it's the model of acetaminophen-induced liver damage. So the AST, ALT, and INR fit to this family of curves that only depend on the overdose amount and the time since overdose. And so that gives us an estimate of the dosage and timing of the overdose. And then we get outcome by asking if the estimated time since overdose and the overdose amount predict death. So does 70% hepatic necrosis occur? And then independent of that, is creatinine high? So is there sufficient kidney damage? I told you kidney damage is also important in determining survival. So that's a little separate from the model, but it'll give us outcome. Okay. So if we do that for all 53 patients that we have data from using only the data on admission, so it's only the very first data point, their AST, ALT, INR on admission, we can estimate the overdose amount in grams on the x-axis and the time since overdose in days on the y-axis for each patient. Okay, so this gray line is the line that separates predicted recovery from predicted death, and it corresponds to 70% hepatic necrosis, right? So it's parameterized so that a 20-gram overdose gives 70% hepatic necrosis. But then also, if there's early enough treatment, so if the time since overdose is early enough, then the 70% necrosis hasn't yet occurred, and NAC will rescue the patient. Okay? So that's where this curve comes from. So each of the dots on here, each of the points, represents one patient, and it's color-coded and shape-coded based on eventual outcome. So patients who eventually recovered are green circles. Patients who eventually died are these red squares. And patients who are eventually transplanted, there are only 2, are these orange triangles. And then on top of that, patients with high creatinine, I've put a small black dot on top of. So there are a few patients that happen to have high creatinine. Okay, so we see that the model does a pretty good job separating patients who eventually died, so these red squares, from patients who eventually recovered. So most of the patients who recovered are in this predicted recovery zone, and most of the patients who eventually died are in this predicted death zone, right? So it does a good job separating. It misses a few patients. So this one's right on the boundary, and it happened to get it wrong. This patient actually survived. I don't know why, but they're in the predicted death zone, right? There's some error. These 2 patients died, and the model predicted they should recover, except they had high creatinine. So with the addition of creatinine, maybe they died from kidney function. I don't know. But it also, if you include kidney function, you get these 2 false positives as well. Okay.
There was an outlier point before, right?
This guy.
Yeah.
Yep.
What happens if you redo the analysis without that guy?
This guy, we got it right, though.
No. The question is, does it change the? You're throwing out an outlier point in the model, in the fit.
Oh.
Does it change the structure of the fit?
No, we're fitting each patient individually. So for each patient, for each patient, you get an AST, ALT, and INR, and you estimate for that patient what was their overdose amount in time since overdose. So where do they live on here?
Yeah, but that box itself, the model itself was fit using all the patient data, right? No?
No. No, the model,
Weights were.
that's only the weights for AST, ALT, and INR. So that's just for the weighted least squares to estimate that. That's using post-treatment model data. So that's a little different. That's just so that we can do the weighted least square to get the overdose amount in time since overdose.
But to get a predicted overdose amount that high, would the AST, ALT, INR data that went into that from that patient have been an outlier?
Potentially, but not necessarily. I'd have to look at it. I'm not sure. I'm going to show you confidence regions in a little bit for these patients, and I don't know if you'll be as concerned about this patient after I show you some of the confidence regions, actually. I don't know how much time I want to spend on this, but this is the current criteria that people use to determine if somebody needs a transplant after an overdose. So it's just a statistical method. This is actually a subset of this is what I had access to as part of the King's College criteria. So to meet King's College criteria, you have to have both high INR, so greater than 6.5, and high creatinine, so greater than 3.4, as well, and then separate from that, or high arterial pH, and then in addition to this, high or bad coma score. But I don't have access to coma score or arterial pH in my data set. So this is what I have access to. But only one patient actually met King's College criteria, if you think of it as the full King's College criteria. Only this one patient met the criteria. And they actually did die, but it didn't predict these other patients to die, unless you think of it as either or, which is not how the criteria is written. But if you were to think of it as either high creatinine or high INR, then it actually does an okay job separating patients. So we can compare our model results to King's College criteria, looking at specificity, sensitivity, PPV, and NPV, positive predictive value, negative predictive value. So MDs like to look at this. I bet a lot of you are familiar, some maybe not, but just briefly. So sensitivity is of the patients who actually died, what is the fraction that the test says that they should die? Specificity is of the patients who recovered, the fraction that actually did recover. And PPV and NPV have different denominators, right? So it's of the patients that the test result predicts to die, actually died, and of the patients who eventually recovered, actually did recover. So if we compare King's College criteria to our model, both with and without creatinine, and King's College criteria, thinking about it as either or, we get this table. So King's College criteria, like I said, only one, or like you saw, only one patient met King's College criteria. So they have quite a low sensitivity. Only 1 out of 8 patients that died was predicted to die. But they had a very high specificity because they predicted everyone would recover. So they got all the recovered patients correct. Thinking about it as either or, they did much better. Our model also did quite well. And with the addition of creatinine, we got all of the patients who eventually died correct, though there were 4 false positives. So there is a trade-off, right, to including creatinine. But our model did pretty well separating patients from who eventually died from those who recovered. But yeah, this is what I wanted to show you, Lou, when you were asking about the individual patient. So if we zoom in on patient number 5 who actually recovered, and plot so this is the patient who was that particular dot. So they were predicted to have had an estimated overdose amount that was fairly high, but not high enough to be on the wrong side of the death line, and a fairly late time since overdose. But these are the other time since overdose and overdose amounts that give a reasonably good fit. And we see this characteristic L shape. So the model has a hard time distinguishing patients who had a higher overdose amount, but very early treatment, from those who were later but a lower overdose amount, right? So you get this L shape. But in both cases, they're predicted to recover. So for outcome, maybe it doesn't matter as much. Okay, so I also have plotted the ALT, AST, INR, and creatinine time series. So more about this. So this is a confidence region for time since overdose and overdose amount. So it's a least squares problem, right? So we're looking at these are other overdose amounts and time since overdose that also give a good fit to the data, okay? And the color is based on how good the fit is. So the best fit is from this orange point. These are good fits. I'd have to look specifically at how I shaded it, but it's within it's a 95% region, right? But yeah, the colors go out as the fit is worse. Okay, so we only use the data on admission, right? So we're using ALT, AST, and INR on admission. So the data point on admission is this black filled-in circle. And the estimated point then from the model is this red filled-in circle. And the time series then, so each of these are another measurement of the patient. Okay, so we see actually really good fits for the rest of the time series using only the data on admission. So that's a good check that we have the dynamics somewhat right? So the ALT, AST, and INR actually fit the time series for the patient using only this data point on admission. Okay. So if we do the same thing for another patient, so this is number 8, another patient who recovered, who was predicted to have a fairly high overdose amount and about 2 days since admission, or since overdose to admission. We see again quite good fit for the time series of ALT, AST, and INR using only this data point, the first data point on admission. And it got the result right, so this patient also recovered. This is a patient who was predicted to have had a much lower overdose in about 2 days since overdose. Again, you get this characteristic L shape, but it's closer to the, even closer to the recovery zone. So none of this region is in this predicted death area. And you see much lower values of INR, AST, and ALT, but again, the fits are pretty good after treatment. This patient only was admitted to the hospital for a day and a half or 2 days. So the time series isn't as long, right, because they recovered, which is good. And finally, one patient who actually died, this is patient number 49, and they were predicted to die, so they were predicted to have a high overdose and a late time since overdose, so the NAC treatment wouldn't work. They had a very high INR value, and again, the fits post-treatment, we have a number of data points, and they fit fairly well. So it misses a little bit on it overestimated ALT, but overall the fits are quite good. Okay, so just a summary of this section. So we developed this dynamic mathematical model that only depends on the time since overdose and the overdose amount. So we can estimate the time since overdose and overdose amount from patient data that's available on admission. And so the estimates are based on this overdose amount. The estimates of outcome are based on this overdose amount, time since overdose, and then also this addition of creatinine because kidney damage matters. So the model does pretty well compared to King's College criteria in our little data set. It's only 53 patients, right? If you wanted to actually say something about how this did to King's College criteria, you'd have to have a much larger multi-center data set, which we'd love to do. And the estimates of outcome aren't very sensitive to model parameters. So I didn't show you anything having to do with this. But if you do a mini sensitivity analysis and perturb all the parameters by 50% plus or minus, the estimates of outcome don't change very much at all. A little bit for a few parameters, but not that much. The estimates of time since overdose and overdose amount do vary based on certain parameters. So for instance, the fraction of acetaminophen that's converted to NAPKI matters for the overdose that causes death, right? So if more NAPKI is produced for a given overdose amount, then a lower dosage will lead to death, but the whole thing scales. So it's really an effective dosage that we're estimating. Okay. But what happens with chronic use? So I told you in the very beginning that historically there were typically one-time overdoses, but more often about 50-50 these days, people are having acute liver failure, so rapid liver failure from chronic use of acetaminophen, so overdosing over multiple days. In the model, so we fit patient data based on a single-time overdose model. So you can easily throw in some sort of acetaminophen production term or intake term, sigma, into the model. And if you do so, you can solve for the steady states in terms of this acetaminophen intake, grams per day, for acetaminophen, NAPK, glutathione, and hepatocytes. You can actually solve for the steady states analytically, though they're very ugly, and you can get their stability numerically. So black are the stable steady states, and red are unstable steady states. So let's focus down here on hepatocytes for a given intake rate in grams per day. We see that there are, for low levels of acetaminophen intake, there's either a no damage steady state, so H equals 1, so there's no damage, or there's full damage, H equals 0. And there's a separatrix that separates these two. So there's either no damage from chronic use, constant chronic use, or there's full damage from constant chronic use for low intake rates. But for low intake rates, the no damage case associated with that, we have decreasing glutathione, low levels of NAPK, and low levels of acetaminophen in the blood. For high levels of a chronic intake rate, the only stable state is full damage. And associated with that, we have very high levels of NAPK, high levels of acetaminophen, and almost no glutathione, though intracellular concentrations don't make a ton of sense if you're talking about no liver existing, right? Okay.
Can we relate the grams per day to actual dose?
Yeah, so typical.
Really high.
Oh, these are, so the therapeutic dose, I should have mentioned this in the beginning. So the therapeutic maximum dose in the US is 4 grams per day. It's not 4 grams at once, but 4 grams over the course of a day. Though they've been talking about lowering it, and I'm not sure if that actually went through. The FDA has talked about lowering it to 3 grams per day. Other developed countries have also lowered the recommended dose to 3 grams per day.
500 milligram.
Pills, typically, the large pills, I thought they were 500, but maybe they're 600, but somewhere around there are the large pills. They also have smaller pills, so it varies.
So this is only 2 more pills per day.
That's what for these parameter values. This is for my parameter values. No, and I mean that is an interesting thing actually for acetaminophen in general. Is there's a narrow window between the therapeutic dose and the dosage that causes hepatotoxicity, and that's actually known. So if it were to be approved now, I'm not sure it would get through quite as easily, right? Because the dosage that leads to death, it's thought, is only a factor of 5 more than therapeutic dose, which is really not that much. So it's a scary window, and that's known. Yeah, so for these parameter values, this bifurcation occurs at about 7 grams. Yeah. So let's zoom in then on this bifurcation diagram. And okay, so it looks like these are straight lines, but they're not quite. So if I play with gamma, so gamma is the binding rate of NAPK to glutathione. So glutathione binds very rapidly to NAPK, right? Glutathione is very good at its job, binds very rapidly to NAPK. If I lower glutathione, we can see what's actually happening here a little bit. What we have are a pair of saddle node bifurcations for those mathematicians in the room. And if you take the limit as gamma goes to infinity, these 2 saddle node bifurcations collide, and that's why you get the straight lines. They collide into a single transcritical bifurcation in the limit as gamma goes to infinity. And the reason that's nice is because you can take the limit as gamma goes to infinity and actually solve for where this bifurcation point occurs in terms of parameter values. And it makes sense once you get it, but it doesn't really, you don't get it until you do the math. It corresponds to the ratio of glutathione synthesis to NAPK production. Okay, so that's where this point is. That's where the bifurcation occurs. So for areas here, for sigma lower than approximately 6.9 grams per day, there's more glutathione. So the glutathione synthesis rate is faster than NAPK production. And for sigma greater than this bifurcation point, there's more NAPK being produced than there is glutathione being produced to conjugate it. Okay? So an interesting question is then what happens at areas very close to this bifurcation? So if we look at starting with no acetaminophen use initial conditions and then have chronic constant use of either 6.5, 7, or 7.5 grams per day. So 6.5 is less than the bifurcation. So I have plotted here acetaminophen, glutathione, NAPQ, and hepatocytes over time. So for 6.5 grams per day, it's below the bifurcation value. There's no damage that occurs. Okay? So H stays very close to 1. So it's normal value. But glutathione rapidly gets depleted, not all the way to 0, but close to 0. Acetaminophen stays low. NAPQ stays basically at 0. But above the bifurcation value, so at 7 or 7.5 grams per day, H makes this transition from the stable state of 1 to the, well, there's only one stable state for values above the bifurcation, and that's 0. And it makes the transition in a matter of days. So it happens very rapidly. So in the model, liver damage happens very rapidly if it happens at all. Okay, so that's why even with chronic use, there's acute liver damage, not chronic liver damage. It's really hard to balance NAPQ production to glutathione production. So either the liver's being damaged rapidly or it's not being damaged at all. Okay, so that was just thinking about constant chronic use of acetaminophen. Now I want to make a couple of scenarios that have time-varying acetaminophen intake or decreasing glutathione production rate. So we have this separatrix separating these two stable states. It's known that glutathione production rate might vary between patients. So for instance, people who are malnourished they can't synthesize glutathione quite so quickly. And so this might lower for some reason, for some amount of time, and initiate liver damage. So 3 of the scenarios I want to talk about involve constant acetaminophen use and followed by some overdose of some size. Okay? So there's either constant acetaminophen use followed by an overdose of size A over, and then continued constant use for a day and a half followed by no further use, or no further use following the overdose. And then 2 scenarios involving decreased glutathione production. So constant acetaminophen use and then decreased glutathione production for a day and a half with continued constant use, or constant use is decreased to 0 after glutathione production increases to its normal value. I'm going to skip these. So the question we really want to ask with the model, with these scenarios, is the following. So can we estimate outcome from chronic use data using our single overdose model, right? So the model I showed you earlier is based on a single-time overdose. And the patient data that we got, we don't know if it was a single-time overdose or the result of chronic use. So we can try to answer this using synthetic data. So we numerically solve these time-varying scenarios for a range of parameters, so a range of chronic intake rate, a range of overdose amount, and a range of decrease in glutathione production, and then make the synthetic data by saving the AST, ALT, and INR, and then minimum hepatocyte level for a range of time since overdose. Okay, so this gives us, just going across all these different parameters, it gives us a ton of different synthetic data points. And then we can see if these synthetic data points from the chronic scenarios actually fit the single-time overdose model to get a time since overdose, an overdose amount, and a minimum hepatocyte level. And then what we really care about is outcome, right? Because in some of these cases, there is no single time of overdose or overdose amount. It's a result of chronic use, right? But we do want to know if the minimum hepatocyte level that we estimate actually matches the real minimum hepatocyte level. So to make this make a little more sense, this is just an example for one synthetic data point. So this is scenario 2 for a chronic intake rate of 5 grams per day, an overdose amount of 12 grams, and the data comes at 3 days post-overdose. That's when the patient comes to the hospital. So I have plotted here hepatocytes, INR, AST, and ALT for the scenario. So that's the black curve. And so the data point on admission is black, which is hidden because the fit was actually really good in this case to the single-time overdose model with an estimated overdose amount of 22.9 grams and a time-since overdose of 2.45 days. So the timing is off, right? The actual time since the overdose, since chronic use, was 3 days. The estimated time was about half a day earlier. And the overdose amount was estimated to be much larger. But that makes sense because this patient also chronically used acetaminophen. So they took more than just this overdose amount. So the fit's really good for this patient. If we do that for all of our synthetic data points, so if I told you we made synthetic data points from a wide range of parameters, made 3,100 synthetic data points, and then fit them to the model, the estimated minimum hepatocyte level matches the actual minimum hepatocyte level really well for all 5 scenarios for almost all the parameter values. And when you think about it, it actually makes some sense because liver damage happens either acutely or not at all. So the dynamics of hepatocytes follow a similar trajectory regardless of if the overdose is from chronic use or from a single-time overdose.
But it's all based on the model.
The chronic use, yeah, but the synthetic data comes from chronic use, and the estimated outcome comes from the original single-time overdose model.
Chronic was the same model.
Same model. Yep. Okay, so this is what I talked about earlier. We developed this model that connects the intracellular metabolism to cellular marker dynamics, and then use that to estimate time since overdose, overdose amount, and outcome from patient data. So if you look at the model dynamics for chronic use, you have this simple threshold with respect to liver damage and acetaminophen intake. So there's either no damage or damage is occurring rapidly. And that's because so the liver damage is generally acute because it's really hard to exactly balance NAPK production with glutathione synthesis, right? It's really hard to actually take an acetaminophen value that would exactly balance the amount of glutathione production. So the liver is either being damaged rapidly or not at all. But when we also look at the steady state, there is something bad even if there's no liver damage occurring. So chronic use is associated with decreased glutathione levels. And glutathione is your body's main antioxidant. So that may have implications for somebody who's a true chronic user for disease, right? Because if you don't want to have chronically low levels of glutathione. And this is pretty important. So the outcome is accurately estimated from the synthetic chronic use data using the single-time overdose model. So and that is just because the liver injury is generally acute even with chronic use. It's surprisingly accurate. Okay, so back to this diagram. So we can really think about this as a really simple multi-scale problem, right? Where we have intracellular biochemistry that connects to the cellular dynamics and then things that you can actually measure. So last December, Mike Reed's group, so Mike Reed and Fred Nyhout's group at Duke, so they connected more detailed acetaminophen metabolism model, so more detailed biochemistry of acetaminophen metabolism model to our cellular dynamic model to answer some different questions. But they include much more detail of the different pathways of acetaminophen metabolism and also connect this. So they've spent a lot of time modeling glutathione synthesis. So in my simple model, glutathione synthesis is just a parameter, right? It's a constant rate. They're actually looking at, so this is GSH. You can see the complex cascade of events that produce glutathione. And this is useful because they're trying to, so their model is really complementary to ours in that their detailed biochemistry really lets them look at how a variety of factors affect acetaminophen metabolism, things like diet, genetic polymorphisms, expression levels of enzymes. But their cellular dynamics for a given overdose amount are really similar to ours, which is also good. So the model is really complementary to ours. So our simple model is sufficient to estimate the timing and dosage and predict outcome, but this detailed model allows you to ask a different set of questions. I think it's interesting work. Okay, and I know a lot of you in this room are ecologists, and you are very disappointed that I didn't talk about ecology today and I talked about medicine. So I have one slide, because I know you thought acetaminophen metabolism has nothing to do with ecology. It has a tiny bit to do with ecology, at least. So the brown tree snake in Guam, some of you have probably heard of. It's a classical invasive species system. I see people nodding their heads, right? So it's native to this region, Australia, Papua New Guinea. But it was introduced to Guam after World War II, probably in military transport ships. And it just wiped out native species on Guam. So it decimated the population. Some 10 of 12 native bird species went extinct. There are now some 2 million brown tree snakes in Guam, and they're biting kids, and they're biting dogs, and the ecology is all screwed up. And they're also climbing electric poles, and there's a lot of power outages because of this. So the USDA has this plan. They've actually done it once. So they did this in 2010, and they're going to do it again either in April or May of this year. So the news articles were all out in February. But they're planning to airdrop dead mice that are laced with acetaminophen and fitted with parachutes. They're not quite parachutes, but they're fitted with things that make the mice snag in trees. So these snakes are unique in that they'll eat things that are already dead, rodents that are already dead, and they live in trees. So you don't want the rodents on the ground. You want them to be in the trees. So they fit these dead mice that are laced with, it's a child's dose of acetaminophen. So acetaminophen, the mice can't metabolize acetaminophen well. A child's dose is enough to kill a snake. So they're dropping them by helicopter, and it's apparently somewhat effective. Yeah. So it's an interesting story related to ecology. Yeah, so I need to acknowledge funding, NIMBioS, and my collaborators. So I worked with Fred on this, and also Norman Sussman, who's a hepatologist, a liver surgeon, who really got me interested in this project. And Lindsay Wattups and Terry Box helped with the data from the University of Utah. So thanks.
Other questions?
Okay. So what do the snakes take for pain?
Advil. No, I don't. That's funny.
But about your model,
Uh-huh.
where is it metabolically? Is it, I'm not quite sure, is it the same for everyone, or it has individual parameters?
So as the model is currently written, there's just one set of parameters, right? But if you actually, there's certainly going to be individuality in certain parameters, right? That's an avenue I would love to research further. It's not clear that it would actually affect outcome predictions. Yeah, but it would affect so things like there are genetic polymorphisms that make it so a much higher fraction of acetaminophen will be metabolized to NAPGI for certain individuals. So they just really can't process acetaminophen well, and they're much more likely to have an overdose from a small amount.
So you say this risk prediction outcome very insensitive to your
Yeah, it's not that sensitive to parameters, and the reason for that is because the estimates of dosage and time since overdose are coming from the patient data itself, right? So the effective dosage is really built in. If you have levels that make it look like a high overdose, then it was a high overdose for you, right? It may not have been a dosage that would cause liver damage in somebody else, but so it's kind of built in. Does that make sense?
In other words, if you're capable to metabolize it better, you won't even come with the symptoms.
Well, yeah, if you don't have any reason to go to the hospital, you're probably not going to. But
So the people who come already have some symptoms that should be measured.
right. Although in our data set, we didn't filter it. So some of the other data sets, people have filtered based on AST and ALT. I mean, they define acute liver failure as opposed to acute liver injury as being sufficiently high. But
Probably, again, there is a big spread of how people can metabolize, depending on that.
right, so certain parameters will have a lot of variation for individuals. That's true. But I am saying that maybe doesn't matter as much for predicting outcome. It matters for, the dosage that you're estimating might be wrong. So if you were to make twice as much NAPQ than a given person, than a normal person, for a given dose, then you might have twice the liver injury about than a typical person for a given dose. So it would estimate your dosage wrong, but your effective dosage would be twice as much, I guess, than a given person, because you're making that much NAPQ. The estimates really derive from the amount of unconjugated NAPQ, right? That's what really matters.
Ask a question about the data. I wanted to make sure. It looked like that data set had about 53 patients.
53 exactly, yep.
And there was 500 deaths per year. That must be over a number of years.
Yeah, these data come from University of Utah only, and they're over a number of years. I don't remember exactly. No. It's 5 years or so. They get.
There's a significant number of deaths, and I didn't think Utah was different from the rest of the country.
So they have a transplant center there, though. So it is for the Intermountain West region, they do get a lot of people who. So the people may not have. This may not be the very. They may come from Idaho or something, and then they're very rapidly.
Have they been treated somewhere else?
Well, I'm trying to remember. It's been a bit. We filtered. We got those patients. Those patients are not in this study. Yeah. So this is when it was patients who. So even if they come from Idaho, they may have. I mean, if they were sufficiently bad shape, they were transferred very rapidly before NAC treatment. But yeah, that would be something you'd want to worry about.
Well, I was just wondering if you could get I always think about spatial differences.
Oh.
Whether you could get regional differences in response based on just data like that in terms of percent deaths versus.
Yeah, if I were to overdose on Tylenol, I would not want to be, and I would not want to go to a small hospital necessarily that isn't used to dealing with it, because they don't always have NAC on hand. It has a short shelf life. It's reasonably expensive. It's not that expensive, but they just don't use it that often, right? So it's common, but it's not that common. And they don't always know how to. They don't recognize it right away. So by the time the patient comes in, they may have low levels of acetaminophen in the blood, so it's not obvious that it's acetaminophen overdose. But yeah, I don't think I have those data in this data set to look at spatial differences. That would be another really interesting question, right? We're currently so.
Done that? Sort of just look at spatially differences in success. There must be.
Yeah. So King's College criteria works incredibly better at King's College than anywhere else. No, but the UK patients may actually be different for whatever reason, right? They may have. So in the U.S., we have more chronic patients than chronic cases than in Europe in general. So the UK, I think this is right. I think it's the UK. They recently made it so they don't have big bottles anymore. They have tabs that you have to push out. It's hard to push out enough tabs to actually make yourself. So it's a really simple fix, right? But that makes people presumably less likely to overdose. Yeah, Sergey.
General question. So what was the most challenging part here in this project? A lot of different things.
Parameterizing the model is always challenging, right? Figuring out the exact right. Yeah, and then exactly what the hard part is always what's the question, right? In modeling, what question are you trying to answer? Yeah. So in this case, I think it was figuring out all the parameters and then how to use the data correctly. Yeah.
What about how you apply the results from your model? When you've got a predicted outcome,
Yeah.
is that actually used to decide how to treat patients?
Well, so if this were validated, right? So the dream would be to validate this and have it just work beautifully, right? And if that were true, then you could easily code up something for an iPhone or an iPad or a computer where you'd just plug in AST and ALT and INR value, and it would spit out one of these plots for the patient. Right? You could do that right then for a patient, right when you got the lab values.
Which would potentially say, this guy doesn't have a chance, I shouldn't.
Well, or say they need a liver transplant. It would potentially, it might get them on a liver transplant. So it's really hard. Yeah, I mean, allocating. There's a limited supply. It's a really challenging problem because unlike most causes of liver failure, acetaminophen overdose patients typically recover. Right? You saw 50,000 cases in the emergency room, but they look really bad. They have really high INR, really high AST, really high ALT. The damage happens very rapidly, but then they recover very rapidly. And they almost all spontaneously recover, but some don't. So the surgeons don't want to waste a liver. There aren't that many. And it's much better to have your own liver than a transplanted one. So they don't want to, they're hesitant to put these patients on the transplant list unless it really is bad. So the goal is early prediction, right? Predicting what's going to happen to the patient before it gets so bad that it's obvious that they need a transplant and it's too late. Yep.
This may have been in your slide, and I just couldn't take it in the time, but the predicted values of your model versus King's College.
The predicted
values.
Oh, yeah, there's a...
Were they both on that?
They're on that little table, yeah. So King's College itself didn't do very well at all for this data set for whatever reason.
About predicted values. Those are the
Positive, this is positive predictive value. Is that what you're talking about?
Yes.
This is PPV. And negative predictive value, yep. Yeah, I guess I talked mostly about sensitivity and specificity. But so the actual King's College criteria didn't do nearly as well for our little data set as the either-or. I don't want to extrapolate too much. I think our method's interesting in that it's a completely different approach than a typical statistical approach, right? We're using a dynamic model based on what we actually know about liver damage. So I don't think our data set's really big enough to say that much here. Yep, Dan.
So to kind of think of this from just a statistics point of view, your model basically takes three-dimensional input data and projects it into two dimensions.
That's right.
Right?
Yeah, I guess.
It gives you a decision surface as well.
Yeah.
Have you looked at how that compares to like something like just logistic regression or something with no dynamics behind it? And would you be interested in comparing?
So when you just do a multiple regression using AST, ALT, and INR, it doesn't even have, typically, you don't even find that AST and ALT are significant. And that's because the dynamics matter. They don't strictly increase. Right? So you need to have some sort of nonlinear model where these increase and decrease.
So,
yeah.
so
Am I missing something?
Even like something with one nonlinear layer in there.
Yeah. I haven't done it. No, I'd love to talk about it. Okay. I'm not a statistician, so I would love to talk about it. Okay. People haven't tried that many fancy things, though, with these types of data. I mean, King's College just did multiple regression.
Your method ends up being the transformation from 3D to 2D is very
Yeah,
nonlinear,
that's interesting.
right?
Yeah, it is. Totally is.
That's kind of the big strength of it.
And so you figure out the nonlinearities based on what we know about metabolism.
Right.
Yeah. Yep.
I want to ask, concerning your feeding for the different individuals in the same area, you sort of feed the same set of parameters for these different individuals for each data set.
So the only parameters we're estimating from a patient value are time since overdose and overdose amount. So those are what we're getting for each individual patient. Everything else is fixed.
So just like feeding two parameters?
Yeah, we're just fitting the two parameters. They're interesting parameters because it's a dynamical system and one of them is time. So it's a little weird, right? And one of them is an initial condition, which is a parameter. But so it's a little weird. But yeah, you're just getting the two parameters.
Initial model where you're saying the set of parameters that runs from each feature and just put the parameters that are known from each.
Oh, there. Here.
Yeah.
Oh, very simply, just scaling so that the betas are such that the well, things like this. No, it's not no fancy fitting going on here. So things like a 6-gram overdose is equivalent to glutathione depletion. So I just scaled the parameter so that that's true, and I scaled the parameter so that a 20-gram overdose causes 70% necrosis and death. Yeah, there's no fancy fitting going on at all. The only fitting is to get the weights, and then once you have the weights for each individual patient, it only depends on the time since overdose and the overdose amount, those two things. Yep.
Do you think the alcohols would change a lot if you include alcohol?
Alcohol. So alcohol is interesting, right? Because so people don't exactly know why alcohol is bad with acetaminophen, but it's probably bad in two ways. So it's thought to, it potentially increases the cytochrome P450 activity, which makes it so you make more NAPK for a given dose, and it potentially also uses up glutathione. And a lot of other drugs might compete for glutathione, right? And so that's how alcohol would come into play. I think it would be another one of those. It would be similar to like a malnourished patient who has decreased glutathione production, and it would just be patient-specific parameters. But yeah, alcohol is definitely something it seems to be not acute alcohol, though, but chronic alcoholics are the ones who have trouble processing acetaminophen. So it is definitely interesting. It's another one of those patient-specific things. Okay.
Let's thank Chris again.
Thanks.